Okay, so I've been telling you about diagrams, but not just any old diagrams. They're young diagrams. And today, I'm going to actually sketch out how you use them to classify representations of groups, starting with the sort of the king of all groups, which is the symmetric groups, the group of permutations of a finite set, and then moving on to other groups. So we're going to classify the irreducible representations of the symmetric groups, Sn, for starters, using Young diagrams. So let me just remind you of some stuff that I said last time that we need to have fresh in our minds. So there's some things that work for any finite group. So if G is a finite group, there's a couple of theorems that imply that its group algebra is isomorphic to something simple, semi-simple. So it's group algebra. By definition, what it means is you take formal linear combinations of group elements with coefficients A sub G here that are complex numbers, and it's obvious how to add those, and then you multiply them using the multiplication in the group G, and so you get an associative algebra this way. And then the theorem says that this is isomorphic as an algebra to some algebra of block diagonal matrices. And this is the key to understanding the irreducible representations of the group G, because it's very easy to get matrices to act as linear transformations of a vector space. So for example, this is sort of going to be our running example. If you take, and I've told you this before, the group algebra of the permutations of a three-element set is isomorphic to a block diagonal matrix. Sorry, it's isomorphic to the algebra of block diagonal matrices that are 4 by 4 matrices, but they have this kind of block form. So there's a 1 by 1 block, and then another 1 by 1 block, and then a 2 by 2 block, like this. And we'll say more about that. But the point is that in general, each block gives you an irreducible representation of G. So let me say it like this: each K by K block gives an irreducible representation of group P. And the way it works is just that you take your group element and then you think of it as a special element of the group algebra, because just a lone group element can be thought of as an element of this vector space here. And then what you can do is you can project down to that K by K block. So that is, if you know that this is isomorphic to some algebra block diagonal matrices, you can project that big fat matrix down to any one of these particular blocks. Just throw away the rest of the matrix. And so then you just get a linear transformation of C to the K. That's what a K by K matrix is. And so this composite here is a bunch of monoid homomorphisms. Each one is a monoid homomorphism. And so the composite is, and so you get a monoid homomorphism from G to linear transformations on some vector space. And that's just what a representation of a group is. And the key fact that's also non-obvious is that you get all the irrets of G this way. That's actually maybe not too hard to prove once you believe this other stuff. So we get all irreps of G up to isomorphism. That's all we really care about this way. So one for each block. So for example, as soon as you know the group algebra of S3 looks like this, you know it has 3 irreducible representations. So the question though, yes.
There's a question on Zoom.
Okay.
Is that projection to the block related to the induction restriction adjunction? I suppose projections like restriction.
It's not about induction or restriction of group representations. It's a, you could probably think of it as restriction of algebra representations. So, but it's not so much about the stuff that people normally talk about when they're talking about induction and restriction, which you usually hear about for group representations.
Okay.
Yeah. So the big question though is how do you find these blocks? Because I'm laying it out for you here as if it was obvious, this isomorphism here, but that's exactly what's not obvious. So the big question is, how do you find the blocks? How do you find the isomorphism to a block, to an algebra of block diagonal matrices? So now we have to think about what group we've got. And so for a permutation group, a symmetric group Sn, these correspond to n-box Young diagrams. And so I have to tell you how. So once you believe that, then you will believe that we get one irreducible representation of our symmetric for each n-box Young diagram. And we'll sort of see how that works. So that, as always in mathematics, if you're trying to figure out how to get something, it's very often good to pretend you already have it and then see what it's like, and then you can use that to figure out how you would get it. So let's pretend we already had these blocks, and notice that each block contains something which is called a minimal idempotent. So for example, in our example of the group S3, we had these various blocks, and in the upper left-hand block, you could just stick a one there, and I'll call this guy pi1, and that's an example of a minimal idempotent. For the next block, you do the same trick. Anything that I don't write is a zero that has to be a zero because we're dealing with these block diagonal matrices. So I'm going to try to save time by not writing so many zeros. So that's a minimal idempotent. The only time it gets a little more interesting, where you actually get a choice, is when you get to this 2x2 block, because when you get to this 2x2 block, there's no God-given rule that says you should put a 1 here or a 1 down here. That would just depend on our ordering of the bases. But just for kicks, I'll put it up here. And that will be yet another minimal idempotent. But this last one here makes it really clear that these minimal idempotents are not unique. So what do I mean anyway, though, by a minimal idempotent? Well, maybe you already know. An idempotent is just a fancy name for something that when you square it, you get itself back. And you can see that any of those matrices that I wrote down there, if you square them, it equals themselves. So they are idempotents. let's pretend we've got this list of these minimal idempotents. But what idempotent means is that one of these guys, when you square it, you get it back. Minimal is more subtle and interesting. So there, in this third block here, there'd be lots of idempotents. For in particular, we could have stuck a 1 in both diagonal slots. We get the identity matrix there, and that's idempotent. But we're trying to sort of make the smallest kind of idempotent we can, and that's what the minimal business means. So minimal means that your idempotent is not the sum of some other idempotents. But more precisely, it's not the sum of idempotents except for itself in 0. Where 0 is idempotent. So there would still be lots of choices. I want to keep emphasizing, I guess, that they're of minimal idempotent, and except in these 1-by-1 block pieces, there are lots of choices. So because there are lots of choices, we need to say something or other that ensures that we're picking just one of these minimal idempotents per block. And we need to say this in a way that doesn't assume we already know what the blocks are. I mean, if you see the blocks, then it's too easy. But what we're trying to do is get to the situation where someone can just hand us a group algebra, and then we can find the blocks by running around using our godlike powers, finding all the idempotents and then finding the minimal ones, and then like making sure we've got just enough of them, not too many and not too few. And so for the not too many part, so to get just one idempotent per block, what we'll do is we'll demand that there's what I call separated. There's probably some official name for this. And I don't really know it. So I just made something up. Separated. But what does that mean? It means that if we have two different of these idempotents, well, first of all, we want their product to be 0, but much stronger than that. We want it to be that if you multiply one of them and then anything in your group algebra and then another one, that you get 0. So this is true for any element A in the group algebra if I is not equal to j. So if you think about it, in these, it's true in these examples. When you have an idempotent in one block, when you multiply it by any A here, you get something that's still in that block. Whatever Tom's doing is much more exciting.
No, sorry.
Okay.
Technical.
No, it's good. You have someone explaining the final theory of everything, and then like a puppy runs in, forget it, no one's gonna pay attention. And so you see that, like, if this is in one block and that's in another block, no matrix that you can stick in the middle will make them give you something in the same block. They can sort of talk to each other, so you always get 0. So that's the separated condition. Sorry. Yeah.
There's a question on Zoom. Why do we want minimal idempotents and not maximal idempotents in each block? It looks like a huge question. I would love to use the maximal idempotents.
Those are just the central idempotents, the idempotents that commute with everything. If I had taken a 1, 1, 0, 0 in this block, that would be a maximal. Well, I mean, the maximal idempotent would just be the diagonal matrix with all 1s. That's the identity. So that's actually not good. I mean, that's an answer. That's a sufficient answer to that question why we don't want maximal idempotents. There's just one maximal idempotent. It's the identity matrix. Boring. Okay, but you could ask, like, why do we want to do this sneaky trick of minimal idempotence when there's something else that's like more canonical, which is to take minimal central idempotence, one which commute with everything. And then we get a one, and then the one matrix here. But we'll see why we don't want to do that. And I'd be glad to talk about that a lot more later, like afterwards, because it's sort of lengthy. So then, okay, so now we like make sure we don't have too many. And so we just want to make sure we don't have too few. And so for that, we'll just take a largest possible set of separated minimal idempotents. Now, the usual word for largest possible in math is maximal. And somehow having maximal and minimal in the same sentence makes me nervous, but tough. Okay, so the theorem, which I'm not proving, is that irreps of a finite group G correspond to minimal idempotence I in a maximal separated set of these. These and minimal idempotence. So the way it works is sort of like the matrix example indicates. So the I irrep of G comes from left multiplying on a certain vector space that we can build up out of our group algebra and the idempotent, namely left multiplication by elements of G, which remember are in this group algebra, on this vector space we get, which is this: you take your group algebra and you multiply it on the right by the idempotent. And so if you think about it, the picture is this. I just like look at one block. So like here's all the stuff in one of those blocks. And then if I'm multiplying it by my minimal idempotent, I'm not drawing the whole big fat 4x4 matrix because the rest of it is just going to get killed anyway. But when I do this, I get a bunch of matrices, and the matrices I get form a column vector. So a k by k block is going to give you a k-dimensional vector space like this, and left multiplication on the left then is going to give you a k-dimensional representation of your group. So that's the story.
Just on this separated condition, you sort of spoke about how we can see this for these matrices. For sort of a general algebra, do we expect there to exist a sort of a separated set of elements, even if we don't consider idempotence?
Well, I mean, whenever you have a semi-simple algebra over the complex number, it has this kind of thing. You can find these separated sets of minimal idempotence. So it's a sort of general thing about algebras. I mean, semi-simple algebras, and this is an algebra of that type, and so you get this. So I mean, there's a lot of stuff you show to show these things, but yeah, that's how it works.
I have a similar question.
Yeah.
So these idempotents are in the group algebra themselves.
Yeah, they're in there.
Not if you forget matrices even exist. Like
Right. Yeah, the whole point is like I said, it's sort of like you pretend you know what you pretend you have what you want, and then you use it to do stuff, and then you prove using that and a lot of work that you can get what you wish you had. Right. So we started out with this we really started with this group algebra, all these concepts, minimal idempotence and separated set just make sense in any algebra, right? So there's nothing to do with block matrices. But then if you puff and you puff, then you can show that when you have this situation, then your group algebra has to be isomorphic to a direct sum of matrix algebras. And the way you get those matrix algebras is by this procedure. You get these vector spaces, and then your group algebra is acting on those vector spaces. So that means that you're getting maps from your group algebra down to different matrix algebras, one for each block.
You could write these as almost sums of actual permutations rather than matrices.
Sorry?
I don't want to belabor it, but
I mean,
you could write
here-
them as formal sums of abstract permutations.
Yeah, that's what's really going on. That's what's really going on. The matrices are just the crutch to help us understand how we would ever think of a crazy sounding theorem like that. Yeah.
Zoom question. In the theorem, are the irreps so got all different for different min idempotents?
Yes, so you get one separate irrep for each idempotent, you get all irreps that way. And it's really easy to see that they're different if you believe this story about that the situation is isomorphic to block diagonal matrices, because matrices living in different little blocks just act in completely different ways on these vector spaces here. So well, you can show it. It's true. Okay, so now I want to get to this is like general stuff for finite groups. So then how do you get this to work? How do you get these minimal idempotents in the case of the symmetric group, which is what we're really interested in? And so the theorem there, which is this theorem is just sort of announcing what we're going to do, and then they have to fill in more details. So irreps of Sn, i.e., well, sorry, let me put it this way. So we get a maximal separated set of separated minimal idempotents. In the group algebra of the permutation group from n-box Young diagrams. I'll tell you how we do this, but that means that we're going to get one irreducible representation of the permutation group for each n-box Young diagram. And by the way, these idempotents have a name. They're called Young symmetrizers. But I need to tell you what they are to make this theorem more interesting. So here's how you get them. So I'll take an n-box Young diagram, and I'll sketch out how to build an idempotent from it. So there are lots of n-box Young diagrams, of course, and it's big. And let me just draw one. So let's say like it has 4 boxes in the first row, and then 3 in the second row, and then 1 in the third row, and 1 in the fourth row. So what we'll do is we'll pack it with numbers in 1 through n in the most obvious way, well, one of the most obvious ways, going across the rows like this, 7, 8, 9. So that's what we'll do. And then what we'll consider is permutations. So you can permute these numbers with any element in the group S9 in this case, but there's certain special kind of permutations that are important. Some permutations will only mix up numbers in each row. Others will only mix up numbers in each column. So those are important. So let R, which is going to be a subgroup of Sn, be the permutations that preserve rows. They don't mix a number from one row to another row. And then let's see, do the same thing for the columns. So this is like preserving all the rows. Preserving all the columns. Now it turns out that from each of those two subgroups, we can get ourselves an idempotent in a sort of simple manner. And then we can combine those two in a not at all simple manner to get the idempotent we really want. Well, the manner is simple, but the fact that it works is amazing. So what is this? So the idea is we get some idempotents from this. For one of them, I'll just call P. It depends on which Young diagram we pick. And so what we do is we just symmetrize over all rows. That is, we consider all possible permutations in R, we sum over them, and then we divide by the number of them. So we just sum over all permutations in this subgroup R. And this sum here is a sum that makes sense in the group algebra. So we get an element in the group algebra that way. And you can see by how we've done things, if you think about it a bit, that this is an idempotent. If you square this thing, you get a double sum where you take like products of all pairs of row permutations, but then that's just giving you all possible row permutations, but you're like over counting them by a factor of how many row permutations you have, but that's why we stuck this in here. So you can see right away P squared is equal to P. And then there's another one. Well, this one is, you might think I was just going to do the same thing for the column permutations, and I could. That would give me another idempotent. But instead, you play a fiendish trick. We do what's called anti-symmetrizing over the column preserving permutations, meaning that instead of just doing this sum we had before.
And you mean C?
Yes. Thanks. Instead of just doing that, we multiply each permutation by its sign. So we add all the even permutations that preserve the columns and then subtract all the odd ones. It's the main thing you need to know is that the sign of a product of permutations is the product of their signs, and the signs could be plus or minus 1. And so if you know that, then you can just like square this thing, and you can see that you get back the same thing. Just like a little easy calculation if you know this fact. So we get again an idempotent. So those are two ways to get an idempotent from this guy. But it turns out that these are not minimal idempotents. So what we want to do is sort of combine them to get sort of a smaller, in some sense, idempotent. And there's this amazing theorem that PQ, so if you do, you could do this in either order, but I'm going to do PQ. PQ is going to be proportional to a minimal idempotent. So it's not a minimal idempotent, but if you multiply it by the right number, you get a minimal idempotent. So that should be quite surprising. It would, if P and Q commuted, you'd be in heaven, because then you could just do PQ squared, switch some P's and Q's around and use this, and you get this PQ. But they don't commute, okay? They do not commute. So we do not get an idempotent typically. So it's amazing that we get something proportional to an idempotent. And the usual proof you see in a book on representations of the symmetric group is that they just calculate the bloody thing and keep track of everything and show that yes, it works out. It's very unsatisfying if you think that this is supposed to be like divine mathematics, and all of a sudden it's like you're sort of fighting your way through the trenches of summings over complicated bunches of permutations. But it's an amazing theorem. And yeah, and so let me call this something like, I don't know, pi. I mean, it depends on our Young diagram. And these pi's give this thing we're after, this maximal separated set of minimal idempotents. So I, for years, wanted a more conceptual proof of all of this stuff. I mean, especially this, actually. I mean, so a lot of this stuff so far have not been has pretty good proofs. This really deserves something better. My friend James Dolan, when I told him about this just like a few days ago, he said, like, oh, I know a better way to do this stuff. That's it. You just do da 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 da. I won't try to explain that because it is probably is better, but it requires more concepts. So I should get the, and also he hasn't like written up a proof or anything. So I'll have to think about that. But this is what you'll normally see. So let me just give you some examples. Very easy examples. So in fact, I'll just stick to my favorite permutation group S3. So if I wasn't showing off, I would say like I'm studying the representation theory of S3, but yeah.
By these pi's, we mean pi's arising from different diagrams, right?
Yeah, that's right. Yeah, that's right. Yeah, so for all, yeah. So all the n-box Young diagrams. So in other words, I'm making good on my previous claim. Yeah.
While I've interrupted you, there's a question from a little while ago. That theorem you had up there before about irreps, is that true over non-algebraically closed fields?
That, I really only want to be, yeah, so this is why I love the complex numbers, right? This is why physicists use the complex numbers, so they don't have to answer questions like that. So it turns out that like for symmetric groups, this stuff would work over any field of characteristic 0. But for general finite groups, which I think was the theorem that was sitting right there, then it would be true for in the algebraically closed case only. Yes. And yeah, and if you're not, God, yeah, I think that's true. Man, you're really mean. Yeah, I think that's true. Yeah. So a whole bunch of stuff I've been doing has been assuming algebraically closed characteristic 0, and I might as well just say face it, complex numbers. But yeah, but it is very interesting to think about these other cases. So for example, if you're doing finite fields, working over finite fields, nobody knows all the irreducible representations of the permutation group now of the symmetric groups even today, unless someone just discovered it like today. So it gets much harder there. Okay, so we're having enough fun already. So in this case now here, the column permutations are trivial. This is like our first Young diagram of the 3 that you get for S3. So I'll call this guy Q1. So the Q that we get there is just the identity. We're summing over just the identity because it's just that's the only column permutation. P1 is interesting. It's all permutations preserve this row. So we're just summing over all the permutations in the permutation group in this case. And this would be called something like complete symmetrization. We're just summing over all the elements in the permutation group. And so our guy that I maybe call pi1 it's P times Q, but Q is 1. So it's just this. It's just this pi 1 here. So it's just completely symmetrizing everything. And then notice that if you do any permutation and then do pi 1, if you multiply this sum by an extra permutation, you're still summing over all the permutations, just in some different order. So you just get pi 1. So what that means is that if you take any linear combination of permutations and you multiply it on the right by pi 1, you just get a multiple of pi 1. So this is going to be just one-dimensional. This is just multiples, constant multiples of pi 1. So that means we're getting a one-dimensional rep. So we get a 1D irrep from this guy. And because of this fact, it's the trivial representation. It's just the 1D trivial representation where all the group elements act trivially. Trivial because it's not doing anything on the elements of that. So okay, that's fine. Every finite group has that irrep, the trivial irrep, where it's one-dimensional and all the group elements that map to the identity transformation. More interesting is Y2, the tall, skinny Young diagram. So in this case, all the row permutations are trivial, and it's just the column permutations that are non-trivial, and everything is a column permutation. But here we're getting the sign in the definition here. And so these are 2 now, we're up to 2. And so here pi 2 is just the column thing. And this is called complete anti-symmetrization. These two, the tall, skinny, and the short, fat ones, are the only really easy ones to understand. Because of this kind of fact that it's, in these cases, P times Q is not just proportional to an idempotent, it actually already is an idempotent. And so here, in this case, something similar happens, but here, if you do sigma followed by pi 2, you're sticking in an extra permutation, but the sign issues gums things up a little bit, so you get minus pi 2. But apart from that, it's very similar. In particular, this vector space here is still one-dimensional because
the sign of
what?
the sign of
The sign of the permutation. Thank you. For some stupid reason, I had in my mind about something like an elementary transposition, but right, thanks. Thanks very much. Good. So you still get that this is one-dimensional, and so what we get is a famous 1D irrep called the sign representation, which just is a 1D irrep where each permutation just acts as multiplication by its sign. So those are the two representations of the permutation group that are easy to understand, the two irreducible ones that are easy to understand. Everything else is much more of a mess, and that's why the theory of Young diagrams exists, is to handle all the other cases except for the tall, skinny, and the short, fat Young diagrams. So I'll just say a tiny bit about the most important piece, which is this one here. So now there are non-trivial row and column permutations, and all hell breaks loose. So our minimal idempotent in this case, it's just proportional to the product of row symmetrization and column anti-symmetrization. So I could write it like this. So when we do the row symmetrization, I'm going to write permutations this way, where I write them by taking the numbers in this box and actually permuting them. So if I permute the row, there's just one row where we can do some interesting permutation. These are all the row permutations, and I'm dividing by 2 because there are 2 of them. So this is the thing. This is what it's called P1 or P3, I guess. And then there's this kind of thing for the columns. And so you can see, like, it's already getting annoying. That is, if you're hoping that like everything is simple. So you can multiply this out and you get linear combination of 4 permutations. And if you're feeling ambitious, you can check. Well, you can check that if you square this thing, you get some number times the same thing. But that's already annoying, right? Because you have a thing that's a sum of 4 terms and you're squaring it. So it's not, you begin to get the sense of like how it's tough to prove this type of theorem. The way they prove it is they just sort of basically do that in general, do that type of thing in general. That is to write out a thing like this, an arbitrary thing like this, for example, square it and you show you get something proportional to itself. It turns out that this, and I'm not proving it at all, this gives a 2D, or I should say the 2D irreducible representation of S3. So it's already less obvious that it is 2-dimensional. What it is. Well, let me just tell you what it is. Oh boy, I'm taking too long to do everything, but anyway, hopefully it's clear. So I should at least tell you what this irrep is like, a different way to think about it. So one way to think about this irrep is you take an equilateral triangle and you draw it centered at the origin in the plane. And the great thing about an equilateral triangle is its symmetry group is S3. It has 3 vertices, you can permute them. So S3 acts on this triangle and therefore it acts on the plane just by sort of carrying the plane around with the triangle. Imagine you just like drew a triangle on a piece of cardboard. And so it's acting on R2. So S3 gets an action on R2, but then you can just complexify. Think that R2 is sitting in C2. So it acts on C2. And so that's this 2-dimensional irrep of S3. It's just coming from the symmetries of a triangle. So you get a similar thing from like there's a nice irrep of Sn where it's acting on an n simplex by permuting the vertices, and then you turn it into an irrep this way. I wish I had beautiful geometrical descriptions like that of all the different irreps of all the permutation groups, but I don't. Okay. Yes.
If you reverse P and Q, do you get the same thing?
No, they don't commute with each other. Yeah. See, if they commuted with each other.
Well, they can commute up to a constant.
Oh.
Right. There's a proportionality in that, right?
I don't think so. I'm not completely sure that they don't, but I suspect that they don't. And you know, we should suspect that they're like wads of choices of these minimal idempotents. And so this, I suspect we get like a different idempotent if we adopted that other convention. Everything would still work, but it would just be like a different set. I believe. Yeah, I don't think they commute up to a constant. That sounds too good, much too good to be true. So, okay. So now I want to just give a taste of what is coming next. And I won't really get too far. So the cool part is that Young diagrams actually can be used to classify irreps of lots of groups. In particular, these groups called the classical groups. So what's a classical group? Well, there's no precise definition of a classical group, just sort of, it's a lot like classical music, in fact. So if I asked you to mathematically define classical music, you would have a lot of trouble. But you certainly know some classical composers when you see them, and that's the same with classical groups. So the idea of classical groups is that they are that these guys are symmetry groups of vector spaces. So they're groups of linear transformations of vector spaces that preserve some nice extra structure on the vector space. So, of course, the weasel word, that was very precise, right? Except for one word, the nice part. And so that's why some groups are sort of more classical than others. But it's also why, in some cases, everybody agrees. So I'll tell you a little bit, just a tiny bit, about 4 classical groups.
John, you asked me to wave at you at 10 to.
Yes. Okay, so I will stop soon, but I want to introduce these 4 characters here. So if you're taking notes, I'm deliberately writing down here. So this guy here, I think I'll cheat by not writing everything down on the board. Is that okay if you give out lecture notes? Okay, so this guy here is called the general linear group. It's the group of all linear transformations of C to the n. All invertible linear transformations of C to the n. That's the most classical of classical groups. It's basically preserving only just the fact that it's the vector space, the linear structure itself. Then there's this guy, SLNC, the special linear group. That's a subgroup of the general linear group, as the name might hint. And this is the guys, the transformations that have determinant 1. So special means determinant 1. So these are all linear transformations of C to the n with determinant equals 1. So Young diagrams can be used to describe the irreducible representations of both these guys, but also other guys. There's another incredibly important classical group, which is the group of n by n unitary matrices or unitary linear transformations. So these preserve the usual inner product on C to the n. And an inner product is sort of exactly what I meant when I said a nice structure on a vector space. And then there's the intersection of UN and SLNC, and that's called SUN. So those are unitary and determinant 1. And that's also called the special unitary group. So it turns out that all of these can be, the representations of all 4 of these incredibly important groups can be classified using Young diagrams, but each one has its own slight wrinkle attached to it, which I may say a little bit about next time. But I just want to conclude by saying that the whole reason why I brought monoids and not just groups into the game is that this group here is actually sitting inside an important monoid, which is just the monoid of all linear transformations of C to the n. And group representation theory books, because they're written by these people who like groups, never think about, they never study the representations of this monoid, except perhaps implicitly. But this is clearly like the most important thing. And it's called the full linear monoid by those who love it. So it's just all linear transformations of C to the n. And so it turns out that the easiest and most important thing to classify are the representations of that. And when you have an irreducible representation of that, and then once you have an irreducible representation of that, you can get representations of all these other things, because remember, a representation of a monoid is just a homomorphism from it to linear transformations of some vector space. So if I have a representation of this thing, I can just compose with some of these arrows and get a representation of any one of these. So the fact that this guy has representations classified by, turns out, Young diagrams with at most n rows, that's the theorem, sheds tons of light on how you classify all those others using Young diagrams. Okay, so I'll stop there and say a little bit more about it next time. I think next time I will not try to cover all of these. That's all in my lecture notes. I may be naughty or whatever and just only talk about this one here, even though the lecture says classical groups. I think this is the classical monoid that we should really be looking at. Okay, thanks. Any questions? Yep.
When it comes to that last point you make, is there a big difference between representations of NCN as a monoid or as a Lie algebra?
Yeah, there's a huge difference. And then there's like a third thing you can look at it as that's very, very common, which is representations as an associative algebra, right? Matrix, and my matrices really love to be an associative algebra. And if you classify the, well, one thing I should admit is that for all these things, I will actually only be classifying what are called algebraic representations, which means that so you know a representation turns things into matrices. These things already are matrices, and so an algebraic representation is where that matrix entries of the matrix you get from the representation is some algebraic function of the matrix entries of the matrix you started with. So for example, complex conjugation can be used to cook up representations of these things that aren't algebraic. Okay, so I won't talk about those. But if you stick to algebraic representations, then it turns out that if you think of NCN as an algebra, it just has one irreducible representation, which is just the obvious one where it's acting as itself. That is, it's just acting on C to the n in the obvious way. So some kind of spin-off of Vedderburn's theory says that just has one irreducible representation. Now, as a Lie algebra, it gets a much more interesting bunch of irreducible representations. And actually, yeah, now that I think about it, that should be pretty close to the irreducible representations of it as a monoid, actually. I hadn't quite thought about it that way. I think those are like almost the same, actually, now that I think about it. Yeah, I'll have to think about it more, but I think you're right. It's an interesting point. Mm-hmm. Yeah, so any other questions? Yeah.
I have a kind of big question. So here we have Young diagrams which correspond to partitions of n, and they give you representations of AC. So we also have 3D Young diagrams or planar partitions.
Yeah.
Do they also correspond to representations of some group or something?
I don't know. Does anyone know anything about these things? So there are things called plane partitions, which are things like they're like 3D things where you take a Young diagram, you make it into blocks and you set it down on the ground, and then you stack another Young diagram on it that's smaller, and another one and another one and another one. So it's sort of like some obvious way of trying to keep on having fun with Young diagrams, like going up into higher dimensions, and you can like keep on going up into higher dimensions. And it turns out that these things, which for some reason are called plane partitions, I don't even know why they're called that. I would call them like 3D Young diagrams. They show up a whole lot in all sorts of interesting subjects in mathematical physics and fancy kinds of representation theory. But I do not know something like a group whose representations are classified by those. I'd really like to know those. I'd really like to know more about those. Yeah.
A question from Egbert Riker. Is there an analogous correspondence between monoid algebras with finite monoid and non-invertible block matrices?
Non-invertible.
Not necessarily invertible.
Not necessarily invertible. I don't know the answer to that. One thing that came up in the Zulip discussions of this stuff that I'm really fascinated by is like, here I'm like showing off so much, saying like, ha ha ha, all these people are doing groups, but like you should be studying this monoid. And then what have I been telling you about all day? I've been telling you about the group of bijections from a finite set to itself. So if I apply my own philosophy, I should also study the monoid of all maps from a finite sub to itself and try to understand the irreducible representations of that. And I have no idea what you get there. And so I know a guy, Benjamin Steinberg, who has a book on representations of finite monoids. And so I should get a hold of that book and hope that he's studied that example. That may not have been exactly an answer to the question, but that's about as close as I can get, I think. Yeah.
So Andy Baker in chat says Clifford and Preston.
Clifford and Preston. Okay, well, I'll have to write that down or remember it. Yeah, I obviously need to learn more about this type of stuff.
Okay, it's 4 o'clock now.
What?
It's 4 o'clock now.
Okay, so I guess we're done. Bye. Well, I'm gonna go down to the coffee room and talk to anyone who wants. Yep.
Okay.
Thanks for asking those. Zoom